Hello there. In this video we're going to discuss a special method or special technique used for evaluating a special type of integrals, and we're going to use Laplace transforms in order to achieve this, as some people may look at as a clever trick. Now, if you do not know what a Laplace transform is or the identities associated to it, I do encourage you to go over and look at the Laplace transform videos that I have in my differential equations series first. Because if you don't know the identities of Laplace transforms, then you won't be able to use some of these quick shortcuts, if you may. Alright, so let us just quickly recall what a Laplace transform of function is. So let us recall that the Laplace transform of some function of x is equal to the integral from 0 to infinity of f of x times e to the minus x psi dx. So of course the Laplace transform of a function of x turns out to be a function of this new variable psi. Alright, so of course every type of integral that is real that looks like 0 to infinity with an exponential, sometimes it doesn't need to have an exponential in it. Sometimes you can use Laplace transforms in order to find integrals of this special type. So let's work through a couple examples to sort of illustrate how one can do that. So let us assume we have an integral I is equal to the integral from 0 to infinity of e to the 3x times the sine of 2x dx. So the first observation here is that this is an integral from 0 to infinity. The second observation is we have an exponential function, and the third example, or the third observation, is we have some function of x with respect to x here. So if you can make these three quick observations, then using Laplace transforms most likely is going to be a very easy case. So what we're going to do is we're going to let minus psi be equal to 3. So if that is the case, that means psi is going to be equal to minus 3. So if that is the case, then we can rewrite this integral that we have in terms of a very nice form. So that means I is equal to the integral from 0 to infinity of sine of 2x times e to the minus x psi dx. So what I've done here is I've rewritten the original integral as a Laplace transform of some function. So what I have here, so that means I is actually equivalent to finding the Laplace transform of the function sine of 2x evaluated at the value psi is equal to minus 3. And this is where you need to know your Laplace transform identities. So if you don't know the Laplace transform of sine ax, I'm just going to mention it here. So recall the Laplace transform of sine ax is equal to a divided by psi squared plus a squared. So if that is the case, here a is equal to 2. So that means I is going to be equal to the Laplace transform of sine 2x. So that's going to be equal to 2 divided by psi squared plus 2 squared, evaluated at psi is equal to minus 3. So that means I is going to be equal to 2 divided by psi squared plus 4, again evaluated at psi is equal to minus 3. And now we're going to evaluate our Laplace transform at this value of psi. So that means I is equal to 2 divided by minus 3 squared plus 4. So that means I is equal to 2 divided by 9 plus 4, which is 13. So that means, in summary, the integral from 0 to infinity of e to the 2x, or e to the 3x times sine of 2x dx is equal to 2/13. Pretty clever, right? Alright, so let's work through another example that actually doesn't quite look like you can use Laplace transforms on it, but you actually can. So this is going to require a couple special observations. So let's what are we going to call this? I'm going to call this next integral star, because this integral is actually a little special. So let's look at the integral from minus infinity to infinity of sine of x over x dx. Alright, so let's make a first observation here, because of course this is a video about using Laplace transforms, right? So we need to first off work on these bounds to make this look like an interval. Interval from 0 to infinity. So observation number 1. So if we define f of x to be equal to sine x over x, then f of minus x is going to be equal to sine of minus x divided by minus x. Sine is an odd function, so we can pull this minus out, so we have minus sine of x divided by, well, that's just minus x. These minus signs are going to cancel, and we're just left with sine x over x, which is actually equal to the original function. So if f of minus x equals f of x for all x, then that means f is an even function. So if it's an even function, that means it's a mirror image about the y-axis. So if we have some function, then it's going to be sort of mirrored. So if we're interested in the area, say on the total area here, we can actually just break it apart into two pieces. We can find the area here, A, so the integral is just going to be equal to 2 times one of those pieces. So that's one of the special properties of even functions. So if that is the case, so that means we're going to look from 0 to infinity and minus infinity. We're going to look at the integral from 0 to infinity first and then multiply that by 2 to get the area of interest. So let's go back to the problem and look at what we were looking at. So star is equal to minus infinity to infinity of sine of x over x dx. So we've proven that sine of x over x is an even function, so we can split this integral up into two pieces and multiply one of those pieces by 2. So that means star is going to be equal to 2 times the integral from 0 to infinity of sine of x over x dx. So that takes care of the first piece. Now another piece that we're missing an exponential function here, right? So where is e? So we're looking for a minus e to the minus x psi here. Well, notice that there actually is an e here because we know that e to the 0 is equal to 1, right? So what we can do is we can multiply this function by 1 and introduce this e to the 0 observation. So that means this integral star is going to be equal to 2 times the integral from 0 to infinity of sine of x over x times e to the minus 0 psi, or e to the minus x0 dx. And that's going to be true for all x, right? So there's no big deal there. So now we're going to let psi be equal to minus 0, which is of course equal to 0. So if that's true, then that means our integral star is going to be equal to 2 times the integral from 0 to infinity of sine of x over x times e to the minus x psi dx, which we have written this function as a Laplace transform of this function sine x over x. So that means star is going to be equal to 2 times the Laplace transform of sine x over x evaluated at psi is equal to 0. So recall the Laplace transform of the sinc function, or sine x over x, that's just going to be equal to 2 times pi over 2 minus the arctangent of psi. And now we need to evaluate this Laplace transform at 0. And of course, if you're not familiar with this identity, then I encourage you to go over to the differential equations series and look how we actually go about finding the Laplace transforms of functions. And this is a fun exercise. Alright, so I'm going to plug in 0 here. So that means star is going to be equal to 2 times pi over 2 minus the arctangent of 0. But we know the arctangent of 0 is just equal to 0. So that means star is going to be equal to 2 times pi over 2 minus 0, which is just going to be equal to pi. So what does that mean? So that means the integral from minus infinity to infinity of sine x over x dx is equal to pi. And this is a couple examples on how you can use Laplace transforms to find the value of special types or a family of integrals.